All right. So, now we're going to give name to something. Oh, see, there's that mildly angled underline that I can't handle. We're going to give name to something that we've already known. We're going to recall our theory of acids and bases, and this is called the Arrhenius theory of acids and bases, named after the scientist who sort of proposed this as the definition. This is not a new theory. This is exactly how you've always described them. We're just giving it that name now. I don't think I used that term last time, did I? No, so that's new to us. But it's still definitional, which is to say I'm going to make a little T-chart here, and on the left side of it we'll put acids, and on the right side, bases. And according to Arrhenius theory, in other words, according to the theory that we've taught you thus far, how do we define an acid? What's the definition of an acid? Beautiful. Yep, you couldn't have said it any better. So an acid releases H plus ions when dissolved in water. So we say that it is HA. And even if it's a covalent acid, it will become ionic when dissolved in water. This is the form. So this could be any anion, including a covalent compound, right? Citric acid is a covalent compound, but the acidic hydrogen gets released as an ion, which means that the remaining thing will take the charge of what? If we release an H+, the remaining compound, whether this thing was ionic or covalent to begin with, will have what charge? Negative, that's right. And so we say this will dissociate in water into H+ ions and that A- ion, where A is whatever had been there before. Now devoid of that there. And these will be aqueous. They'll be dissolved in water. On the pH scale, how do we know if something is an acid? Yeah, that's right. And really it's from negative 52 to 7. We think of it as starting at 0 or 1 because those are already quite strong acids. But the pH scale actually extends into the negatives. You can have an acid with a pH of negative 3, be an extremely strong acid, but that can exist. So we say anything with a pH less than 7 is acidic. Not that this matters much. How do they taste? Yeah, very good. They taste sour. Good. I wouldn't recommend it, but you have. If you've ever vomited, right? That's your stomach acid making its way up into your mouth. Yep. Yeah, your body just produces hydrochloric acid in your stomach. Mm-hmm.
What would your stomach acid's pH be?
Oh, low, like 1 or 2. Yeah, your stomach has to constantly produce a mucus lining on its inner layer, and if it didn't, it would digest itself. Every once in a while, people will develop a condition where there's a section of their stomach that doesn't produce that lining, and they get horrible burning there. Have you ever heard of a peptic ulcer?
Yes. That's
what happens when your stomach acid eats away at the stomach tissue itself. Not a very pleasant thing. So we don't like that. What about bases, according to the Arrhenius theory? What do they do? Yeah, very good. They release OH minus ions. What do we call those ions? Sorry? That's right, hydroxide ions. So they take the form something B and then OH. And when they are dissolved in water, what we get is that B left over. What charge will that have to have if it's releasing an OH minus ion? Very good. And again, this could be a covalent compound that releases that. More often, we're going to think of it as an ionic compound: sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide, ammonium hydroxide. You can't really get cobalt hydroxides or iron hydroxides or zinc hydroxides because they're not soluble in water. So we won't see those as much. But there we are. On the pH scale, how do they measure? Greater than 7. What about 7 itself? What's that? It's a weird scale. But water contains both H plus and OH minus. So, yeah, it's when they're perfectly balanced. We call that a pH of 7. We'll learn about that in grade 12 chemistry, which you should take. Great course. How do they taste? Very good. They taste bitter. Now, to be clear, acids pretty much are the only thing that activate that sour component in our mouth. So when you taste something sour, you are tasting something acidic. There's a lot of different chemicals that can taste bitter. So not everything that tastes bitter is a base, but every base tastes bitter. Not all cars are Hondas, kind of thing, that kind of thing. Not every car is a Volkswagen, but every Volkswagen's a car, unless it's a van. I guess that's a bad example, but you see what I'm saying. Anyway, it's like how not every computer is a Chromebook, but you guys wouldn't know that. It's my ultimate pet peeve. I have a Chromebook? No, I don't have Chromebooks. I have a classroom. Sure. Anyway, that's not what I say. What I say is yes. What I think is, Anyway. It's just weird to me. It'd be like if somebody went to like a Ford dealership and like, I'm interested in purchasing a Jeep. They'd be like, well, shouldn't you be over at the Jeep dealership? I would like that Jeep, and points at like a Ford Focus. That'd be weird, right? People come in, they're like, I want a Chromebook, and what they mean is they want one of these, and you know what these aren't? They aren't Chromebooks. That's right. Anyway, that's right. There's computers, the laptops, the Windows devices. What brand are they? Are they Acers?
I think so. Maybe?
Or the Asus? Yep. The other one, yeah. Anyway, whatever. The point being, they suck, but they suck a lot less than the previous ones. Have you noticed that? A substantial improvement. Like dramatically so. The trackpads on the previous ones we had, those HP ones, like they were so upsettingly bad. Like you'd try to, like anything you tried to do with that trackpad would fail. It made me very upset. Okay, and a reminder about the pH scale is a logarithmic scale. You don't need to know what that means. Of the concentration of H plus ions. In fact, it's a negative logarithmic scale, for what that's worth. You don't need to worry about that. But what you basically need to know is that what that means is that as we range from 0 all the way up to 14, and again, I don't even like that framing of it because it implies that like you can't go below 0, which you absolutely can. This isn't there, but if we look at this very even scale that I've drawn that perfectly evenly describes, any one step on it represents what kind of change? Do you remember? Every step is multiplying by 10. So pH 4 isn't 1 stronger than pH 5. It means it's 10 times stronger, which means how much stronger is pH 3 compared to pH 6? No, multiplying, right? So times 10 again would be 1,000. That's the way a logarithmic scale works. So an acid that has a pH of 3 is 1,000 times stronger than an acid that has a pH of 6. A base that has a pH of 11 is how much stronger than a base that has a pH of 10? 10 times, which means a pH of 14 is how much stronger than a pH of 9. 9 to 10 would be how much stronger? 10 times. 10 to 11 would now make that, or 9 to 11 would now be 100. 9 to 12 would be 1,000. 9 to 13 would be 9 to 14 would be 100,000 times as strong. So the pH scale, this is why when we work with acids that are pH 3, I don't make you wear goggles, I don't make you wear things like that. Even yesterday's lab where I had a pH 2 acid out there, I'm not terribly concerned about it, right? Then the next lab we do where I have a pH 0 acid out there, you're going to be in goggles, not just glasses, and we're going to all have gloves on and lab coats, because it's not 2 stronger or 2 times stronger. pH 2 up to pH 0 is 100 times as dangerous. Does that make sense? So that's what you have to be mindful of. And the pH scale can be a bit of a disservice in some ways to that. Does that make sense? Because it can sound like, well, what's the difference between pH 2 and pH 1? That sounds pretty similar. But it's not similar. It's 10 times as dangerous, right?
So Leonard, you didn't get the memo? We're not supposed to teach anything new today either.
Oh, or the day after,
Or the
right?
day after.
This whole semester, right? This is an achievement
Stop
semester.
learning. Just
Listen, they did that the moment I walked in the door. How you doing?
I'm a little tired. It's my own fault. Instead of making my grade 10s test like I should have after work.
Did you stay up all night
my
coding?
Python Farmer Was Replaced game competing against the cactus sorting algorithm leaderboard. This is a fun challenge.
I believe that.
I would
How'd it
explain
go?
I got 25th on the leaderboard of going like hundreds. So
There you go. That's pretty good.
And the number, like I had it down to like 16 something seconds.
Yeah.
There's a few 15s and 14s, but the two number 1 and 2 are like 9 seconds. So they must have a fundamentally different method.
Yeah.
Because you can harvest a cactus if the one to the north and east is a greater size or less than, and when you plant it, it's 10 sizes randomly between 1 and 10. And you have an operation to swap north, swap east, swap south, swap west, and you can measure the one to your left, north, south, east, west, and so on. So you have to, and it's recursive. So if you harvest a cactus and it's in order sorted around it, south and west have to be smaller than it, north and east greater than it, it harvests the whole box, and then it's recursive. And so if the whole field is sorted, it harvests the whole field, and that's the leaderboard, is how fast you can harvest the whole field of cacti.
Interesting.
From planting to harvesting. So it's an algorithm of sorting efficiency. My kind of game. So,
Yeah.
Yeah. It's all Python. It's a game. The Farmer Was Replaced. The game on Steam. If anyone's interested, highly suggest the game. Yeah. I think it's like that, $9, but you learn to code Python. It teaches you to code while making the game as you unlock stuff. And the ultimate leaderboard is automating your entire farm from like 1 block to like unlocking the leaderboard again from start to finish without touching it.
Oh,
I
interesting.
haven't tried for that one because I just like the smaller navigations of solving the maze or planting and sorting cacti.
It's like these people who use AI to like speedrun games.
I don't know how. It's pretty locked down. They keep fixing bugs. Sorry to interrupt.
No, I enjoyed that. But they yeah.
Bye. Owen, how's your college last time?
Anyway, everything above here is really review. That's all stuff we've discussed. Today we're just going to talk, and it's real brief. Like I got a page here, and then stupidly this last page is a note to myself telling me something, so I wasted a whole page to be like, Joe, don't forget to mention this. So anyway, I probably will forget to mention it, because what's going to happen is I'm going to get to the bottom of this page and be like, oh good, note's done, and then I will miss the note to myself, but that's okay. So, how do acids and bases react? Well, acids and bases react and you know the answer to that. Because acids dissolve in water to become an aqueous ionic compound of H plus and something, and bases dissolve in water to be an aqueous compound of OH and something, which means it's a reaction between two aqueous compounds, and you know how two aqueous compounds can react. There's really only one mechanism that we've learned about that. Single displacement, double, right? Because single displacement's an aqueous compound with some sort of solid metal, right? But double displacement is two aqueous compounds. So acids and bases react via double displacement. Now we give it a special name. We call them acid-base reactions, but that is just semantics. The reaction mechanism is one with which you are familiar, double displacement. And we'll give you the general form here. We said that the acid has some acidic hydrogen, so we call it HA+, and then we said the base has its ion OH. And so we don't know what, in this particular case, what species we're talking about, but we know the ions in question. So hydrogen's on a date with its acidic counterpart, and hydroxide is on a date with its basic counterpart. Hydrogen's the cation, OH minus is the anion over here. At the end of this date, if it's a double displacement reaction, who's ending up with whom? Sorry? Hydrogen with hydroxide, which of course would yield us HOH. And we usually write HOH a little bit differently. How do we normally write HOH? Yeah, in other words, if we take an acid and react it with a base, the first product we're going to get is always water. And then, of course, the second reactant would just be what? Ba, and that will likely still be aqueous, But water itself is a liquid, right? So if we take these aqueous compounds and we react them with one another, we're going to get that. So we call this a salt, an aqueous salt. Doesn't mean it has to be salt as you're used to thinking of it, sodium chloride. It just means it's the leftover aqueous components. So that's the general form. So acids and bases react to neutralize one another. Yes, ma'am. That's an AQ. I'm sorry. You can't tell because my Q's are absolutely goofy looking. Oh, well, maybe all my stuff's goofy looking. I don't know what to tell you. When we say they neutralize one another, what do we mean by that? Sure, but they don't just equal each other, they neutralize each other. That's right. If you look here, what made this acidic was that it was an H plus ion floating around. And what made this basic was that it was an OH minus ion floating around. But when that H plus ion bumps into that OH minus ion, what does it make? Water, which is not an H plus ion and is not an OH minus ion. It is a molecular compound now stuck together, which means it is no longer an acid and it's no longer a base. This is why when you mix acids and bases together, they neutralize each other because they just turn into water. And as long as you mix equal amounts, this is a demonstration I wouldn't do for safety purposes, but I could go back there and get 200 mils of pH 0, like deadly dangerous sodium hydroxide, or pH 14 sodium hydroxide, and get 200 mils of pH 0 hydrochloric acid. And if I put it together, I should be able to drink it because it should turn into water. What would it taste like if I did that? Let's take a look at that reaction and see if you can tell me what it would taste like. If I took HCl and sodium hydroxide and I reacted them together, what would it taste like when I was done? Acids taste sour, bases taste bitter. What would the product of mixing them together taste like? Sour and bitter? Neutral, just like water? You tell me. Do the reaction. See what you get. See what you get. Do the reaction.
And I really want to ask about that.
That's what I keep smelling.
It smells good.
This one is like mixed with like 7 other stuff. You suck. Oh my god. It's like a like you can't smell it. And I have like 2 different perfumes on there, like body butter, some of
All right, what's it gonna taste like, team?
salty.
Ah, yeah. If we take a look at it, we take hydrochloric acid, which is really the hydrogen anion, H+, on a date with the chlorine anion, Cl-, and we react that with sodium hydroxide, which is really the Na+ ion hanging out with the OH- ion. When they react via double displacement, hydrogen's not going to be hanging out with chlorine anymore. It's going to be hanging out with OH. And I'm not going to write it as HOH this time. I'm just going to write it properly as water. It actually isn't wrong to write HOH, but it's kind of clumsy. That looks like an E. There we go. That's better. And sodium will now be hanging out with chlorine. And not that I need to do this, but sodium wants to give away how many electrons? Chlorine wants to take how many? So I don't need to draw a chart or anything. The formula is NaCl. We could check our solubility table if we had to, but you should know, does sodium chloride dissolve in water? In fact, you know that anything with sodium dissolves in water, right? So there we go. Now, if I didn't know if it was soluble, where could I check? Where could I check? Yeah, that's exactly right. This, by the way, is what happens. Your stomach produces this. Your small intestine produces not sodium hydroxide. I'm not going to give you that example because it's kind of a weird one, but your small intestines release sodium bicarbonate, and the bicarbonate ion can act like an OH- ion. Don't worry about it. I'm going to hand wave it. Ready? Watch. Just trust me, it works. And that does this same thing where it takes all the acid that leaks out of your stomach into your intestines, which obviously would do damage to the sensitive tissues of your intestines, and it turns it just into water so that it doesn't dissolve your own intestines. Does that make sense? Yeah. I'm ready to know. Let's try another one. Let's try sulfur. Now, this one might need some balancing. Let's try sulfuric acid and, I don't know, potassium hydroxide. Try that one out. See what you get. I think you'll see that these are pretty straightforward. They're all kind of, once you've done one, you've kind of done them all. Now, this does require you to know what sulfuric... Do you see how that line is ever so slightly angled? I know I rant about this all the time, but who was programming this and thought, hey, we'll have it that when you hold it like this, it makes a straight line. Okay, good feature. Oh, and probably what they'll want most of the time is a line that's on an ever so slightly angle so it's not straight. That's what people usually want when they draw a straight line, right? Right? Like, right, Microsoft coders? When a person makes a straight line, what they want is one that is ever so imperceptibly angling up for no reason. Apparently, look, you see it's doing it here too. Like, just why? Why in the world wouldn't it assume that what I want is a straight line? Even that one, like, ever so slightly angles down. I don't know why. Like, that's weird, right? Isn't that crazy? It's crazy. Anyway, work it out. What's sulfuric acid? If we see ic acid, it means right away that we're dealing with a radical. So sulfuric acid is the acid we get with what radical? Sorry?
Sulfate?
Sulfate. Good. So this will be the acid made from the sulfate ion. And do you have to have memorized the sulfate ion? No, but you probably should by now. What's the sulfate ion? SO4, and what charge does it take? And of course, if it's an acid, what's up here? H. And it gives away how many electrons? 1. And we said sulfate wants to take 2. So for these two things to form a compound, well, you can work it out. You know what's going on. You know what's up. You can do the same thing with potassium hydroxide. What's potassium? K. How many electrons does it want to give away? 1. Hydroxide takes how many? Yeah, so you can work that out too, and you can know your starting compounds. Oh my. Hello. Come on in. Oh, it's locked. Is it locked?
Yeah.
I forgot to unlock it today. How's it going? What can I do for you?
Would you like any coffee?
Yeah, you know, this one's ice cold. I would love a coffee.
What kind?
Just black would be great.
Black one, okay.
Yep, thank you so much. Well, yeah, of course. Chemical reaction, right? Hey! Oh, I'm delighted. Well, we'll work on that. Yeah, we'll work on that. But congratulations. That's great. I'm very proud of you. That's wonderful. Shh. It'll work. Almost sounds like you're having fun in my class. You know how I feel about that. Sorry? I'm a hater? That's fair. I'm a party pooper. That would hurt my feelings.
That's literally what you're being a party pooper on purpose, and then your feelings are going to
Doesn't mean you can just call me that. I got news for you. Most of the things we call people, we call them because it describes them accurately. That doesn't mean it doesn't hurt their feelings, right? In fact, if something described you completely, if you were like, Orlando, you're so awkwardly tall it looks weird, that wouldn't hurt my feelings because it's obviously not true, right? You know what I mean? Like, the only reason words can be hurtful is because they accurately describe a person, right? Is that fair? Right? Right? Like, that's the thing we don't like to admit, right? Like, but when somebody says something insulting, the hurtful part is that they're looking at you, sizing you up, finding something that they perceive as a flaw, and then reporting that to you. Right? Yeah. Thank you so much. Now, to be clear, should we care what other people think of us? Well, depends on the context, right? Like, if I'm a teacher and all my students think I'm an ineffective teacher, that should hurt my feelings. But if they all think I have stupid hair, then whatever. That's none of their business what my hair is. Do you know what I mean? Yeah. See what I'm saying? Now, does it hurt maybe a little bit because occasionally my children refer to me as Captain No Fun? Maybe. Which, by the way, is at least creative. Also, is Senor Rules? As in, like, Mr. Rules? Yeah. So, you know. Yeah. Yeah, Mr. Rules. Captain No Fun. These are just some of the ways you can hurt your parents' feelings.
It's really funny.
Yeah. All right, talk to me. What's the formula for sulfuric acid? H2SO4. Good. We need 2 hydrogens because each SO4 doesn't want 1 electron, it wants 2, right? So H2SO4. What's the formula for potassium hydroxide? KOH. Good. Obviously, if these are reacting as an acid and base, then they both must be dissolved in water, and so we put AQ next to them, AQ standing for? Aqueous. Good. On the other side, the H and the OH are going to react how? Yeah, they're going to make water. Now, is it going to be any different because I have 2 hydrogens here? It's still only going to make water. It's not going to make H3O, right? It just means that we're going to have to balance it after. And then what about when potassium starts hanging out with sulfate? Well, we would say, okay, Potassium wants to give away how many electrons? And sulfate wants to take how many? 2. And that means that a single potassium could give 1, 2 potassiums could give away 2 electrons, 3 could give away 3, a single sulfate could take 2, 2 could take 4, 2 could take 6, so on and so forth. We see obviously where they match up. So what's the formula of potassium sulfate? K2SO4, which always sounds to me like it should be a droid in Star Wars. Doesn't it just have that cadence? R2D2 meet K2SO4? Kinda, right? A little bit. Was that too much fun for you? Anyway, potassium sulfate. Will that be aqueous or solid? Not that it really matters, but we could look it up, right? We could go check our little solubility table, and it would tell us that sulfates, as a rule, are soluble, and the only exceptions are calcium, barium, strontium, mercury, lead, and silver. And since we're not making one of those, our product should be soluble. Whoa. And then, of course, water is a liquid, right? The only problem with this is that it needs to be balanced. Here's my advice. Whenever you're balancing something where oxygen shows up here, but also shows up there, hydrogen's in a couple places, you know what I mean? Like, this is messy. First of all, deal with radicals as whole things. Don't think of this as 4 oxygens and then another one there for 5. Do you know what I mean? Sulfate, oxygen's its own thing, right? Keep them separate because these oxygens stay stuck to that sulfur. So just count them there. How many sulfates do we have here? How many sulfates do we have here? So we should just leave that alone, right? Cool. How many potassiums do we have here? 2. How many potassiums do we have here? So what do I need in front? Okay. Now, this is where it might actually be helpful to think of this, even though eventually we're going to rewrite it. This is where this can actually be really useful. Does that make sense? Because how many hydroxides do we have here? 1. How many hydroxides do we have here? So what do I need to put in front? 2. And now, how many hydrogens do I have here? And how many hydrogens did I have here? Does that make sense? So for the purpose of balancing, it can actually be really helpful to think of water as that HOH. Does that make sense? And then, once I've got it balanced, because that looks a little clumsy, I'm actually going to go change it to 2H2O, like that. I'll make that 2 red as well, so we see these are balancing numbers. Now, would it totally work to just count all the hydrogens and say, we have how many hydrogens altogether? 4. And how many do we have here? And how many here? For a total of? That totally works too. So if that's a more comfortable method for you, just do that. But in my head, I often think of the water as HOH, and I find it makes these a lot easier and quicker to balance. Your mileage may vary. Any questions about that? So this is a quote-unquote new type of reaction, but it's not really a new type of reaction. The one thing to note is that covalent acids just leave behind ionic covalent compounds. And what we'll mean by that is this. So for example, we'll look at acetic acid, which is better known as what? I don't know if it's better known as that, no, though that is its formula. It's better known as vinegar, yeah. And we'll do sodium hydroxide. So the way we're going to write acetic acid is as H C2H. I can do this in a second. 5O2. Now, why wouldn't I just write this as H6? Because I'm focusing on the acidic hydrogen. Does that make sense? The truth is, this hydrogen is actually found attached to these two oxygens in the compound. You don't need to know that, but just know all these hydrogens are stuck to the carbon. They're not going anywhere. But this hydrogen that's stuck to the oxygens can't. Am I in the way?
Yeah.
I'm sorry.
Very in the way. Thank you.
You're welcome. Quiet you. You don't need to worry about the fact that this is covalent. You just know that the part of it that's left over is going to take what charge? Negative. And the sodium will take what charge? Positive. So they're just going to end up together. We're going to end up with water, and we'll end up with NaC2H5O2, and that'll be dissolved in water. That'll be a liquid. And because there's only one hydrogen here, this is a nice 1-to-1 ratio. You don't have to worry about that, but it's just the main thing I'm going to knock everything over. The main thing to note is that covalent acids work exactly the same way. All right? Exactly the same way they produce water. They neutralize. If you take grade 12 chemistry, which I strongly recommend you do because it's a great course, I think. I'm biased, obviously, but it's my favorite. It's so wonderful. I'd be teaching it right now, but instead I'm leaving a bunch of lessons online for kids to watch, and it breaks my heart ever so slightly. But that's okay. Hopefully I would, yeah. I mean, maybe it could be Alaschuk too, right? Because he's also qualified. He's more qualified than I am. So one of the two of us. Yeah, but it's a great course. And whoever teaches it, even I can't ruin it. It's just that much fun. I'm not sure of anything now. You've broken my confidence. How do you feel about that?
I think you break it.
My own?
Yeah, I'm just adding on.
Don't blame me.
I'm just adding on.
Don't put it on me. I came here feeling good about myself today. Okay, what I'd like you to do is just write reactions for. Phosphoric acid and sodium hydroxide. A very dramatic Y. Wow. I'm gonna try that again. That's somehow worse. Chlorous acid and lithium hydroxide. Perchloric acid. And magnesium hydroxide. Oh, a dramatic G too. Look at me. And then I want to do a tricky one, a little tricky question. This one is going to combine knowledge from a few different lessons. Because if you remember, in our first lesson on synthesis reactions, we mostly just learned that synthesis reactions are very boring. Calcium and oxygen give you calcium oxide, and sodium and nitrogen give you sodium nitride, and rubidium and chlorine give you rubidium chloride. But we did learn a few special cases. This question is going to make you combine some of those special cases into something. All right, ready? So here it is. calcium metal is burned. Carbon is also burned. Both products are dissolved in water. They react. What are the final products? And show each reaction involved. That's a good question. I've always had this dream. There's a great demonstration I saw once where somebody took sodium metal, which you guys have all seen sodium metal reacting with water. Have you guys not seen that? Actually?
No.
Oh, well, do we have time? We got time. Let's blow something up. Actually, you know what? Is that a good achievement day activity? Yeah, that's a good achievement day activity. We'll blow some stuff up tomorrow. That feels like achievement, right?
Yeah. Tomorrow?
Yeah.
Or tomorrow.
Yeah. So yeah, today you've got work to do. That's fine. We'll blow some sodium up tomorrow. But anyway, don't let me forget. All right, you got to remind me. The other thing is I'm going to throw a link up online to, now that we're through a unit, almost through two, sorry, to your little mark checking app. Should work for you. It should, you just sign in with your DSPN email address. It should take you there. If for some reason it doesn't, just come talk to me and I will figure out I may have typed your email address in wrong or whatever. But that way you can always check your grades on a daily basis, see how you're doing. I like to be very transparent with my grading. Everything on there is given a weight, like how much it's worth, and then you give grade. So if you wanted to, you can sit with the calculator and calculate your grade yourself. But you don't have to. Instead, you can just look it up. But I'm not a big believer in like, use your professional judgment and I don't change things. I just plug them in and then it calculates a number and then that's your grade. Does that make sense? I feel like there's been a trend in education towards like wild and crazy grading systems. And I find those very confusing. I'm not smart enough. So I put them all in, add them all together. I weight them so that they're based on how important they are. And then I press equals and it spits a number out, and that's your grade. Sorry?
Let it happen.
On the final page.
Yes, yeah, my note to myself was about the grading app.
Okay.
So, you're good. See, I even saw it. Isn't that nice of me?
Just around that.
Yeah.
I have a question. So I think for the tricky ones, you'd get a metal oxide and a carbonate, right?
Mm-hmm. Then when you dissolve those in water, what do you get? Before that, when you dissolve both those things in water, another synthesis reaction happens. So go look at the note. If you dissolve a metal oxide in water and if you dissolve a non-metal oxide in water, in each case you get a synthesis reaction to occur. Yeah.
The marking thing, like the SAT, told me to put 2 OHs. I was a little skeptical, but that's what it told me. Savannah told me you told her to put the water.
This is good. Yeah, no. Sorry, that's the marking app doesn't know how to handle this, but that's the right answer.
Okay.
Yeah, no, I'm just going to cross this off,
Yeah,
okay?
that's fine. And I'll give her the mark.
Yeah, sorry about that. Yeah, my marking app didn't know how to deal with formations of hydroxides because you can't just react. OH isn't a thing. Like, OH minus ions are a thing, but there's no such thing as like just take the solid OH off the shelf. The answer is when it's its own thing, it's H2O.
Yeah.
And whoops.
Yeah, alright. And I was having trouble with the spreadsheet, and I got scared, so I didn't enter all the marks. These are all graded.
Oh, great. I'll enter them.
Okay.
Yeah. Can I see what you got scared of? Or I'll disconnect
it's
from here.
just like I would like, put in the mark, but they got like something out of sight, and it wouldn't calculate it. And I was like, I don't want to.
You know what? If you're working online, it does that sometimes.
Yeah.
It will. If you just put them in, you actually, if you want to just put them in,
Yeah.
it will. Is that cool? Because yeah, it will update. It just takes. If you're working on the online version, sometimes it takes loading it on the desktop version for it to update, but it will do.
Okay. That just kind of scared me.
No, you're good. What's up?
I think yesterday, for you, did we get an assignment?
You'll get it tomorrow.
Tomorrow?
Yeah. Sorry, I meant to give it to you yesterday, and I've fallen behind. Sorry about that.
Oh, can you also can you send me the assignment and the lab?
Yes.
Or, okay. What should I do?
The lab I'm retooling, so I'll send that to you today, and I'll send you the assignment, which I'm also retooling. Well, that's what I'm retooling. I'm picking from a menu. I'm not sure which one I want to pick yet.
What's on the menu?
Well, that evaporating one, I've retooled.